So now we're going to talk about the relation between kappa of C, the communication complex C of the problem defined by this communication matrix C, and the rank of C. Okay, and here's an easy lower bound. Kappa of C is at least log of rank of C. Right? So why? It should be very easy. Suppose kappa C is T, right? Well, let's do the induction on T. Right? So if T is 0, then it's trivial. If T is non-zero, then matrix C can be partitioned into two matrices, C1, C2, such that kappa of C1 is at most T minus 1, kappa of C2 is at most T minus 1. Right? Because, for instance, if this was C, I know by the protocol that I will either partition horizontally or partition it vertically, and each of these will have a one less kappa. And by the induction hypothesis, rank of C1 is at most 2 to the T minus 1, rank of C2 is at most 2 to the T minus 1. Now, what is rank of C? Well, it's less than or equal to rank of C1 plus rank of C2, right? Because if you have a matrix obtained by gluing two matrices, rank, like rank is the dimension of the span of the row space in this case, and row space is just the union of row space of each of C1 and row space of the C2. So it's at most that, and that's 2 to the T minus 1 plus 2 to the T minus 1, which is 2 to the T, right? So that's the proof. So this is a simple lower bound on the communication complexity. And remark that recently, until like this, there's a result by Goose and Pitasi and Watson, and they proved that kappa is at least log square of rank of C with some some factor, logarithm factor. So they usually put the omega with tilde, which means that you may have a log of factor, so log of rank. Yes, some function of some polynomial of log rank is also hidden here. So this number 1. So the simple proof gives a log of rank, but they prove that log square of rank is also lower bound. All right, so sometimes even this simple lower bound give a good lower bound. So here's the examples. So equality problem. Right, so you have Alice and Bob. So this is the situation that I mentioned in the previous video. Alice is on Earth, Bob is on the Mars, and they want to check whether their computer code is identical. So each has both got a string, a 01 string of length n. And the question is, are they identical? Right? So Alice has length n string 0, 0, 1, 1, 1, 1. And then Bob also has a length n string 0, 0, 1, 1, 1, 1. And the question is, do we have the same copy? And the trivial protocol, so what is n? So what is the number of states for Alice is like 2 to the n, right? So that's, yeah, so unfortunately I'm using same n, right? So previously n was the number of possible inputs for Alice, but now the number of possible inputs for Alice is 2 to the n. So trivial protocol implies that kappa is at most log 2 of 2 to the n, which is n. That means by sending n bits, you can determine the answer, whether or not they are, I mean, one of them, not all of them, but if Alice send all the inputs, then Bob will know the answer. All right. Oh, no, this is the inequality is the other way around. Trivial. Oh yeah, this is okay. This is no, this is fine. Now let's look at the communication complexity. Right. So we have 2 to the n inputs for of Alice and 2 to the n possible inputs for Bob, and the answer is 1 if they match and 0 otherwise, right? So the rank of C is equal to 2 to the n because this is identity matrix. Rank is a full rank. Now we know that kappa of C is at least log 2 of rank of C, so it's n. So by using this, we can determine the communication complexity of this problem exactly. It's n. All right. Now let me give you another example. So disjointness. So Alice receives a set A, which is subset of 1 up to n. Bob also receives a subset B of set of integers from 1 up to n. The question is does A, B intersect or not? Right? Do they intersect? Are they disjoint? So let's say CN be the communication matrix. Now I want to know what the rank of CN is. What is that? Right? So here are the inputs for Alice, inputs for Bob, right? So this is A, B side, and B side. In A side, I partition rows like this. So these are people having n. Do not have n. No n in the set. And let's say these are people having has n, right? So n is in A. Let me say n is in not in A. Same as that. Oops. So n is in not in B and n is in B. Right? If I partition rows and columns like that, then if both A and B contains n, then they are not if both A and B contains n, then they are not disjoint. So A intersection B is not empty. So that means the answer is 0, false, right? So 0 means not true, right? So A intersection B is no longer empty. And what are other submatrices? And in these three cases, the problem actually reduces to the problem of n-1 situation. Now the element n, in number n doesn't matter because only one of the set contains n. All right. So this is the this is a Cn. Now, what is the determinant of Cn? Because of this old zero matrix part, if I have any permutation, like, determinant is product of these things, right? And you can never use any entry here because, you have to avoid using these zero parts. And the only way you can avoid using that zero part is to use entries here and entries there, right? And you cannot use anything from there. Oh, but actually there's a better way. Just to subtract these rows from these rows and this becomes 0, right? So determinant of Cn is equal to determinant of 0, 0, Cn minus 1, Cn minus 1, right? So it's plus minus determinant of Cn minus 1 squared. All right. So if the Cn minus 1 has non-zero determinant, then Cn also has non-zero determinant. Now let's look at C1. What is C1? If both are empty, then it's 0. If it contains 1, oh no, they are disjoint, so it's 1 and 1, 1 and 0. So determinant of C1 is minus 1. This is the important thing is that this is non-zero. Right? So that means determinant of Cn is plus minus 1 for all n. So that means rank is it's non-singular, so rank is equal to the number of rows, which is 2 to the n, right? That's number of possible inputs, that's number of subsets. So that means kappa of Cn is at least log 2 of rank of Cn, right? And that is n. So kappa is at least n. But also by trivial protocol, kappa is at least at most log of 2 to the n. So that's n. So the communication complexity of this problem is precisely n. Right? So in both problems, we were able to determine precisely what the communication complexity is. Now, let me show you another example. Example 3. This is called the parity problem. All right. So Elise receives a set SAX, set X. So that's an input. Bob also receives a set Y. That's an input. And the question is, determine whether X intersection Y is odd. Right? So we want to know whether it's odd or even. Okay, so how do we decide this? So let's C be the communication matrix. Right, so you have 2 to the n rows and 2 to the n columns. But the problem is that you have a situation where both Alice and Bob receives the empty set. Then this communication matrix will have all zeros here and all zeros here, right? Because intersection is empty set is even. All right, so that means I cannot use the previous technique in this matrix right away, right? The previous technique says that, the previous technique, I use the fact that determinant is non-zero, but now determinant is zero right away because I have a row with all zeros and row with all zeros, the column with all zeros. So let's remove that row. So let's take this as a submatrix. Right? So let C prime be the submatrix of C obtained by deleting the row and the column indexed by empty set. Okay, now let's make some observations. So C prime, what are the properties? So C prime is symmetric, right? Because there's no distinction between Alice and Bob. If you make a transpose, it's still same matrix. Now let's consider the following matrix, C prime squared. So what is that? What does it count? Right. So you have a two matrices, C prime. So we are like multiplying some column of second C prime to some row of the first C prime. So the XY entry of C prime square is what? That is the number of subsets G such that X intersection G is odd and Y intersection G is odd, right? That's the XY entry of the square of C prime. So I want to determine this C prime squared. So if X and Y are equal, then what is that? You have an X which is equal to Y. So how many ways can I pick a set G such that this intersection is odd? Well, that is, 2 to the X, right? That's the number of, I'm choosing that. Oh yeah, but I have to choose other number, only odd size, so half of them will have odd size, and then outside of x I choose any subset, so 2 to the n minus x. So it's 2 to the n minus 1. So these sets having intersection odd. So these are the diagonal entries, right? So 2 to the n minus 1, 2 to the n minus 1. So that's a C prime square. What about the off-diagonal entries? If x is not equal to y, right? In that case, what's gonna happen? Right? I mean, the thing is, all right, so one easy way to count it is among all 2 to the n sets, half of them will have odd intersection, odd number of intersection with x, and half of them has odd number of intersection with y. So this is 2 to the n minus 2. And you can check easily. Right? The thing is the event, I mean, the event that you have an odd intersection with x is independent of the event that you have an odd intersection with y, because x and y are different. So the off-diagonal entries are 2 to the n minus 2. Right? So that's the square. Now, what's nice about it? I claim the C prime squared is non-singular. Why? Because this is same as this made. Right? If you divide each row by 2 to the n minus 2, then what you get is this matrix. All diagonal entries are 2, off-diagonal entries are 1. And why is this matrix non-singular? Why is this matrix non-singular? Well, one way to see it is, so this is non-singular. If and only if, so now it's becoming a simple linear algebra exercise. I'm attaching a new matrix. This is non-singular, right? Because determinant is same. I'm adding one more row and one more column. And the columns are almost all 0 except the one entry on top. And then I put 1 here. So this is non-singular, right? So both are equivalent, right? Because they have the same determinant. But that's same as 1. Now, by using elementary row operations, I can subtract the first row to other rows, right? So I have a matrix like this. So the top one is non-singular. If and only if, this is non-singular. All right. Now, and then add all these rows to top row. I mean, no, subtract all these rows to top rows, then all the entries here become 0, right? And this will become 1 minus some big number. Okay? Which is the number of rows minus 1. Anyway. Oh, no, 1 plus actually. you're subtracting, so -1 times something. So anyway, that's it. This is non-singular. So the problem of saying this is non-singular is equivalent to the problem of saying this is non-singular. But which is non-singular? Because it's upper triangular matrix, no, lower triangular matrix with non-zero diagonal entries. So determinant is the product of the diagonal entries. So we know the determinant. So C prime square is non-singular. But determinant of C prime square is determinant of C prime squared, right? So determinant of C prime is non-zero. So that means C prime is non-singular. Which means the rank of C prime is equal to the number of rows of C prime, so it's 2 to the -1 because we removed one row and one column. So rank of C is 2 to the -1. Now what is kappa of C then? It's the lower bound, so lower bound is log of 2 to the -1, which is again C, then again n, and upper bound is trivially n, so this means the kappa of C is n, right? So what we proved is that for all these three problems, the trivial algorithm is the best algorithm. And there's no algorithm better than the trivial algorithm, trivial protocol. No protocol is better than, strictly better than the trivial protocol for all these three problems. Now, you see, so in these problems, it's nice that you can use the rank function of the matrix to give a explicit proof. All right, explicit proof that the trivial protocol is best possible. Now, you can also give the upper bound on kappa. So here's a position. So rank kappa of C is at most. So it's at least log of rank. Now it's at most rank. Why? This is also an easy fact. If a 0-1 matrix has a rank has rank R, then it has at most 2 to the R distinct rows. Why? If you have a rank R, then there are R columns, right? If you have rank R, there are R columns which spans everything, which span every other column. That means whenever you look at these R entries in each row, then they determine the other entries. And these R entries have at most 2 to the R values, right? So because it's 0-1 vector, so 0 or 1. So these entries in the R columns corresponding to a particular fixed base will determine the whole row vector. And there are 2 to the R possible values. And if you have that many rows, then kappa is at most log of, by using trivial protocol, just send which row block you belong to, right? So log of 2 to the R, so it's R. So that's an upper bound on the communication complexity, right? And so this was all observed by Lovász and Sachs, and they conjectured the following. So this is called the Lowrank conjecture. That states that there exist alpha and beta such that kappa c is at most alpha times log of rank c to the beta. Right? So of course I need the obvious conditions, right? For all 0, 1 0, 1 matrices C. But of course, if rank is 0, then log 0 is not defined. So let's say non-zero 0 matrix. And this conjecture is still open. Right? Here's the best upper bound known. So this is theorem due to Lovett in 2016. He proved that kappa is at most some constant times square root of rank of C times log of rank of C. So you have a big O notation, so you have to assume the rank is big. Or increase the constant huge. So that's the known theorem.